Hello and welcome to the fourth video in our discussion series. For this video, we will be discussing the pH scale. So for us to compute the pH of a particular substance, we will use the formula negative log of hydronium ion concentration. So knowing the hydronium ion concentration is necessary in many different instances. So like in the blood, it must have a hydronium ion concentration in a very narrow range for an individual's good health. So plants thrive in soil that is not too acidic or too basic. The hydronium ion concentration in a swimming pool as well must be measured and adjusted to keep the water clean and free from bacteria and algae. Now, the pH of a solution indicates its relative acidity. In an acidic solution, the pH is less than 7, while in a neutral solution, the pH is equal to 7, and in a basic solution, the pH is greater than 7. So we can see here that the higher the pH, the lower the hydronium ion concentration and the less acidic the solution. So be mindful, most of the students get this wrong by thinking that a higher hydronium ion concentration would be equivalent to a basic solution. Remember, hydronium ions are concerned with acids. So here are some of the pH of our common household substances and some fruits. As you can see, the pH of many fruits is less than 7, making them acidic. And many cleaning agents such as household ammonia and bleach are basic, which has a pH of greater than 7. So here is another diagram showing the pH of different substances. And as you can see here, the blood has a very narrow pH for an individual to have a good health. Now, to determine the pH scale, we have the different values pH, pOH, and the pK sub W. So since the values for the hydronium ion concentration are very small, with negative powers of 10, the pH scale is used to more conveniently to report the hydronium ion concentration. So the pH of a solution is a number generally between 0 and 14, defined in terms of the logarithm of the hydronium ion concentration. So in here, we have pH is equal to the negative log of the hydronium ion concentration, and then the pOH or the pOH is equal to the negative log of the hydroxide ion concentration. So pKW is equal to the pH, or the pKW is equal to the sum of pH and pOH, which should be equal to 14 at 25 degrees Celsius. So as we have established earlier, since K sub W is a constant, the values of pH, pOH, hydronium ion concentration, and hydroxide ion concentration are interrelated. As I have said earlier, if the hydronium ion concentration increases, the hydroxide ion decreases, and vice versa. Likewise, if the pH increases, the pOH decreases, and vice versa. So in calculating the pH, first consider a hydronium ion concentration that has a coefficient of 1 when the number is written in scientific notation. So for example, the value of hydronium ion concentration in apple juice is about 1 times 10 raised to negative 4, or 10 raised to negative 4 written without the coefficient. So since the negative log of 1 times 10 raised to negative 4 is 4, therefore, the pH of that particular substance is 4. So, since pH is defined as the negative logarithm of the hydronium ion concentration, and these concentrations have negative exponents, like in this case, 1 times 10 raised to negative 4, the pH values are positive numbers. Whether a solution is acidic, neutral, or basic, it can now be defined in terms of its pH. An example here, in an art restoration project, a conservator prepares copper plate etching solutions with diluting concentrated nitric acid to 2 molar 0.30 molar, and 0.0063 molar nitric acid. So, calculate the hydrogen ion concentration, pH, hydroxide ion concentration, and pOH of the three solutions at 25 degrees Celsius. So, we remember the nitric acid is a strong acid, so it dissociates completely. We use the given concentrations and the value of K sub W at 25 degrees Celsius to find the hydronium ion concentration and the hydroxide ion concentration. So, we can then calculate the pH and the pOH. So, the hydronium ion concentration here is equal to 2.0 molar. And we can calculate the pH by using the formula negative log of the hydronium ion concentration. So, negative log of 2 is equal to negative 0.30. To calculate the concentration of hydroxide ion, we can divide the K sub W, which is 1.0 times 10 raised to negative 14 by 2, which is the hydronium ion concentration, and we will get the answer 5.0 times 10 raised to negative 15 molar. Now, for the pOH, we can calculate it by using the formula the negative log of the hydroxide ion, which will be equivalent to the negative log of 5.0 times 10 raised to negative 15. And we will get the answer 14.30. So, here are the values for the H3O concentration. We also have here the pH of negative 0.30. And then we have the concentration of hydroxide ion and the pOH. Now, if we calculate the values for the 0.30 nitric acid, so we will have here the hydronium ion concentration, which is equal to 0.30 molar. And then the pH is equal to the negative log of hydronium ion concentration, that would be equivalent to 0.52. And then we can get now the concentration of hydroxide ion by dividing Kw again with the hydronium ion concentration. So we will arrive at the answer 3.3 times 10 raised to negative 14 molar. And then we can also calculate pOH by using the formula negative log of the hydroxide ion concentration, and we will arrive at the answer 13.48. Now, in calculating the values for 0.0063 molar nitric acid, so the hydronium ion concentration is equivalent to 0.0063 molar. So, pH would be equivalent to 2.20, while the concentration of the hydroxide ion is equivalent to 1.6 times 10 raised to negative 12 molar, and the pOH is 11.80. So, from the previous examples, as you can see, if the pOH is higher, the pH will be lower. While if the hydronium ion is higher, the hydroxide ion will be lower. So, here are some of the methods we use for measuring the pH. So, a pH meter is a small electronic device that measures pH when an electrode is dipped into a solution, while paper stripes, called pH paper, change color corresponding to a particular pH when a drop of an aqueous solution is applied to them. So, an acid-base indicator can be used to give an approximate pH, and the indicator is a dye that changes color depending on the pH of the solution. So, here's an example of the common pH indicators when we dip a paper or the pH paper in a solution. So, in the human body, it contains fluids that vary in pH as shown in this figure. So, while saliva is slightly acidic, the gastric juice in the stomach has the lowest pH found in the body. So, the strongly acidic environment of the stomach aids in the digestion of food. It also kills many types of bacteria that might be inadvertently consumed along with food and drink. So, when food leaves the stomach, it passes to the basic environment of the small intestines and the bases in the small intestines react with the acids from the stomach. So the pH of some body fluids must occupy a very narrow range, and for that example, a healthy individual has a blood pH in the range of 7.35 to 7.45. So maintaining this pH is accomplished by a complex mechanism described in your book, as if you can read it, and the pH of other fluids can be more variable. So for example, urine, it has a pH anywhere from 4.6 to 8.0 depending on an individual's recent diet and exercise. So that's it for this part of the discussion series. Thank you for listening.